Next session. Let us discuss partition of a set once again, and then we note these points. Suppose we have a non-empty subset S, non-empty set. So I need to discuss the partition of this. So the partition of this S is defined as sequence of n number of subsets, n number of non-empty subsets of S, such that they satisfy two properties, S1 union, S2 union, and so on union, Sn equal to S. The second condition is Si intersection Sj equal to pi for all I not equal to j. So whenever n non-empty subsets of S, S1, S2, Sn, we have n non-empty subsets. N can be 1, 2, 3, etc. But finitely many non-empty subsets of S. You always consider finitely many non-empty subsets of S, so that when you make union of all these sets, it must cover original set, and intersection of any of two sets must be equal to empty. In that case, all these form a partition of S. When you come to this example, this is general example. This is my set S. I have divided this set S into 4 non-empty subsets. So S1, S2, S3, S4. Basically, S1 is one subset, subset of S which is non-empty. So S1 union, S2 union, S3 union, S4 is S, and intersection of any of these two is non-empty, empty. Therefore, they form a partition. When you go to general example, take 4 element set 1, 2, 3, 4. So S1 equal to only 2. It is a non-empty subset of S. This is a non-empty subset of S, and even this is a non-empty subset of S. So I have divided this set into 3 non-empty subsets, S1, S2, S3. So that, see, division is a silly issue, but you must divide a set into finitely many non-empty subsets of S, so that it covers all set, it covers whole set S, and intersection of any two of these non-empty sets must be empty. So here S1 union, S2 union, S3 is empty, intersection of these two empty, intersection of these two empty, intersection of these two empty. So these 3 sets form a partition of this. Another partition of same set is this. Another partition is S itself. Okay, write these points. Let S be any non-empty set. Let S be any non-empty set. So stop. A partition of S. A partition of S is defined as, a partition of S is defined as finite number of non-empty subsets. A partition of S is defined as, a partition of S is defined as finite number of non-empty subsets of S, finite number of non-empty subsets of S, say S1, S2, and so on, Sn, say S1, S2, and so on, Sn, such that point number 1, S1 union, S2 union, Sn equal to S. Second point, Si intersection Sj equal to pi for all I not equal to j. This is the symbol to be used for all. Union of all these sets is S. Intersection of any two non-empty sets is pi for all I not equal to j. Now you have this example. For the set S, this is first partition, this is second partition, third partition is itself. Note all these partitions. Now we discuss Bayes theorem, followed by factorization, prime factorization of a natural number, and then if time permits, we can discuss classroom workbook, right? Next one is Bayes theorem. Very, very important theorem, Bayes theorem. Suppose we have a sample space S. So sample space is nothing but set of all possible outcomes of an experiment. So all results of an experiment are stored in the form of a set S, that we call it as sample space. Suppose we have two mutually exclusive events. E1 comma E2 are mutually exclusive events. Mutually exclusive events which form a partition of S. Which form a partition of S. So we know the meaning of partition of S. So here E1 and E2 basically they are mutually exclusive events which form a partition of S. What does it mean? E1 union E2 equal to S. E1 intersection E2 equal to pi. So therefore in that case they form a partition. And second point is they are mutually exclusive. That means if E1 occurs then E2 cannot occur. If E2 occurs then E1 cannot occur. Right? So this is my data. S is a sample space. That is all outcomes of an experiment. There are two events E1 and E2 which are mutually exclusive events and they are forming a partition of S. That means E1 union E2 equal to S, E1 intersection E2 equal to pi, and E is any event of S, and E is any event of S such that probability of event is not equal to 0. What does it mean? E occurs always. So probability of E is not equal to 0. That means an event when P of E is 0, that is an impossible event. Impossible event means an event which does not occur always is called an impossible event. But here I am saying that P of E is not equal to 0. That means that event must occur always. But what is original sample space? S. So here S is divided into two parts. This is my sample space. Suppose this is my E1. And this is my E2. So E is an event of S. That means this must occur from either E1 or E2. Now what I discuss is what is the probability that this E is occurring from E1 or what is the probability that E is occurring from E2. That will be described by Bayes' theorem. So then point 1 is P of E1 slash E. That means the probability of occurrence of E from E1. Conditional probability. E is already occurred. E is already happened. Here I am saying that P of E not equal to 0. That means E always occurs. So if E occurs, what is the probability that it occurs from E1? This is my sample space S. It is divided into two partitions. I mean single partition of two mutually exclusive events. If an event occurs from E1, it should not occur from E2. So therefore, if a sample point occurs from E1, it should not occur from E2. If it repeats from E2, it should not be there in E1. So E1 union E2 is S, E1 intersection E2 is pi. Now I am saying that P of E1 is not equal to 0. That means E is already happened. So if E is an event already happened from S, now there are two chances. E may come from E1 or E may come from E2 because this is S only. So E might come either from E1 or from E2. That I will discuss using Bayes' theorem. So P of E1 slash E, this probability is nothing but probability of getting E from E1. Therefore, this is given by P of E1 dot P of E slash E1 divided by P of E1 dot P of E slash E1 or R means plus P of E2 dot P of E slash E2. Now we have two different notations. One is P of E slash E1. Another is P of E1 slash E. This is very clear. Probability of getting E from E1. Now what is P of E slash E1? Probability of getting E from the sample space E1. Because the sample space S is divided into two parts. I am not saying the two equal parts. E1 may contain 30 sample points, E2 may contain 70 sample points if S contains 100 sample points. Or E1 may contain 62, E2 may contain 38 sample points. So that partition need not be equal partition. But so what is this P of E slash E1? Probability of getting E from E1. Now here I wrote differently P of E slash E1. That means E and E1 have been interchanged their positions. So this probability is nothing but probability of getting E from the sample space E1. So here sample space is E1. Now therefore it may come from either E1 or E2. This is a favorable case. This is all possibilities, all possible cases. So therefore this event E may come from E1 or may come from E2. This event E may come from E1 or may come from E2. That means event E is coming from S. So this is all possible cases. This is favorable case. Similarly, I can discuss P of E2 slash E, and this is given by P of E2 into P of E slash E2 divided by, it may come from either E1 or E2. So this is a P of E1 dot P of E slash E1 plus P of E2 dot P of E slash E2. P of E slash E2. So therefore this is nothing but probability of getting E1 E from E1. This probability is probability of getting E from E1, and this is probability of getting E from E2 when the sample space is overall. But here we are getting probability of getting E from sample space E2 only. That's the difference. Okay. So in this case, probability of getting E from E2. What is the probability that E came from E2? What is the probability that E came from E1? But in this case, the probability of getting E from E1 when E1 is sample space. Now for this probability, what is my sample space? E2. But in this case, the sample space is S only. But in this case, the sample space is S. So in this case, the sample space is S. Here also the sample space is S. But in this case, the sample space is E1. And in this case, at this place, the sample space is E2. I hope you understand all these points. Even we can go through examples also. Very powerful this is. Note these points. Bayes theorem. Let E1 comma E2 be two mutually exclusive events. Let E1 comma E2 be two mutually exclusive events which form a partition of a sample space S. Let E1 comma E2 be two mutually exclusive events which form a partition of a sample space S. And capital E be any event of S, and capital E be any event of S such that P of E not equal to 0, and E be any event of S such that P of E not equal to 0. That is, E occurs always. E occurs always. I repeat once again. Let E1 comma E2 be any two mutually exclusive events which form a partition of a sample space S, and capital E be any event of S such that P of E not equal to 0. That is, E always occurs. Then you write this point 1 followed by point 2. 1 followed by point 2, you write these points very clearly. This P is probability of getting E from E1. But to get this probability, sample space is S. But to get this probability, the sample space is even. To get this probability, the sample space is E2. To get this probability, the sample space is S. So if you write these points, things will be very clear. You need not confuse at all. Suppose my sample space S is set of all positive integers from 1 to 15. So divide this into two mutually exclusive events. So let E1 equal to 1, 2, 3 and so on 8. E2 equal to remaining elements, that is from 9 to 15. So 9, 10, 11 and so on 15. So let E be an event of getting an even number. Let E be an event of getting an even number. So what is probability of V? So what is my original sample space? S is 1 to 15. E1 is numbers from 1 to 8. E2 is 9 to 15. Now in this case, E1 is a non-empty subset of S. E2 is a non-empty subset of S such that they satisfy the properties E1 union E2 equal to S, E1 intersection E2 equal to pi. E1 intersection E2 equal to pi. Therefore, E1 comma E2 form a partition of S. E1 comma E2 form a partition of S, and E1 comma E2 are mutually exclusive events. E1 comma E2 are mutually exclusive. You can see no element is common for E1 and E2. So 4 is here but 4 is not here. 12 is here but 12 is not here. No common elements. So if E1 occurs, there is no chance to get E2. If E2 occurs, there is no chance to get E1. So because there is no common element for E1 and E2, therefore they are mutually exclusive events. Now what is E? An event of getting even number. Now let us see. Let us calculate this expression. P of E1 slash E. That means already an event E occurs, because in this case we have even numbers. What is the probability of getting E? How many even numbers are there from 1 to 15? 2, 4, even numbers 2, 4, 6, 8 and so on up to 14. So 7 numbers are there. So the probability of getting even number from this sample space is 7 by 15. But I am saying that what is the probability to get that even number from E1? What is the probability to get that even number from E2? So slightly probabilities will change. If I take probability of getting, if I consider to get probability even number, in case of S, it becomes 7 by 15, because the even numbers inside 1 to 15 are 2, 4, 6, 8, 10, 12, 14, only 7 even numbers. So 7 out of 15. But I am saying that the even number is already selected. So what is the probability that E came from E1? Because even numbers are here. Even numbers are here. So that E may come from either E1 or E2. So I am looking at those probabilities. So probability of getting even number from E1. So this is given by like this. P of E1 dot P of E slash E1 divided by P of E1 into P of E slash E1, or it may come from E2, because in the denominator you need to write all possible cases. Now let us see this. What is probability of E1? See how many points are there? 8 points. 8 out of 15. So P of E1 is 8 by 15 into P of E slash E1. So what is the probability of getting E from E1? So for this, in this case, to get this probability, what is my sample space? This only. So how many sample points are there? In this case, 8 only. How many even numbers are there? 4 even numbers. Therefore, P of E slash E1 is 4 by 8 divided by, this is same expression, 8 by 15 into 4 by 8 plus P of E2. Here 7 numbers are there. So therefore 7 out of 15 into P of E slash E2. So to get this probability, the sample space is E2 only. So how many points are there here? 7 points. How many even numbers are there? 10, 12, 14. So therefore this is 3 by 7. So to get this probability, the sample space is S. But to get right hand side probabilities, particularly this, but only for this, the sample space is S only. To get this probability, sample space S. To get this probability, sample space is S. But to get this probability and this probability, the sample spaces are E1 and E2. That's the only difference. If you understand this, things will be very clear. So to get this probability, the sample space is S. To get this probability, sample space is S. But to get this and this, the sample space is here is E1 and here is E2. So therefore this is 4 by 15 divided by 4 by 15 plus 3 by 15. So therefore this is 4 by 7. So here similarly, when you calculate P of E2 slash E, this is complement of this 1 minus 4 by 7. So this is 3 by 7. Note these points, very important. Suppose if there are three mutually exclusive events, E1 and E2, E3, E1, E2 and E3, which form a partition of sample spaces, then Bayes' theorem can be extended. Then a denominator will be combination of three quantities. The event may come from E1 or from E2 or from E3. Like this, you can extend Bayes' theorem for n number of mutually exclusive events. Okay. Next we go for factorization. Actually, the basic concept behind this is fundamental theorem of arithmetic. Let us see what this theorem states. Suppose we have a natural number n. We have a natural number n. So natural number starts from 1 onwards, but you start from 2 onwards. So n is a natural number which is greater than or equal to 2. So when you take any natural number from 2 onwards, this can be written as product of powers of prime numbers, p1 power alpha 1 into p2 power alpha 2 into p3 power alpha 3 into and so on pk power alpha power k. Now here we have product of powers of some numbers. Here p1 comma p2 comma p3 comma and so on pk are prime numbers, and alpha 1 comma alpha 2 comma alpha 3 and so on alpha k are natural numbers. So that means the power values need not be primes, but base values must be prime numbers. So every natural number from 2 onwards can be expressed as product of powers of prime numbers, and this is called prime factorization of a natural number. So here base values are prime numbers, powers need not be prime numbers. Let us take examples. Suppose if I start with n value, for example 10. Now this 10 can be written as 2 power 1 into 5 power 1. So this is p1 power alpha 1 into p2 power alpha 2. Here p1 is 2, it's a prime, p2 is 5, it's a prime. Example 2, suppose n value is, for example 54. Now 54 can be written as, this we can write it as 2 power 1 into, this is 3 cube. Now this is again in the form p power alpha 1 into p2 power alpha 2. If I take n value like this, for example 35. Now this 35 can be written as 2 into 5 into, this can be written as just 5 into 7 only. So this is 5 power 1 into 7 power 1. This is p1 power alpha 1 cross p2 power alpha 2. So here p1 is 5 and p2 is 7. You know the meaning of prime number. A number which is divisible by exactly two numbers, 1 and itself, is called a prime number. A number which is divisible by exactly 1 and 2. 1 and itself. Sorry, not 2, 1 and itself. A number which is divisible by exactly 1 and itself is called a prime number. Say, what are the examples of prime numbers? 2 is a prime number, 3 is a prime number, 5, for example 17. Even we have some prime numbers between them, 11, 13, like this. So 19, 29, like this. All these are examples of prime numbers. So therefore every natural number from 2 onwards can be expressed as products of prime numbers. So if I express every natural number from 2 onwards like this, I have some advantage. The advantage is we can easily say how many factors will this number have. We can easily guess the number of factors of this number. Okay. So the number of factors of this number is 1 plus alpha 1 into 1 plus alpha 2 into 1 plus alpha k. So this expression gives the total number of factors of this number n. So whenever n has a prime factorization like this, then the total number of factors of this number n is 1 plus alpha 1 into 1 plus alpha 2 into and so on 1 plus alpha k. Why it is so is, if you take alpha 1 value 4, alpha 1 may range from 0 to 4, alpha 2 may range from 0 to 4. Let us take this example, for example 10. 10, what are the factors of 10? The factors of 10 are 1, 2, 5, 10. So this 1 can be written as 2 power 0 into 5 power 0. This 2 can be written as 2 power 1 into 5 power 0. This 5 can be written as 2 power 0 into 5 power 1. 10 can be written as 2 power 1 into 5 power 1. Here alpha 1 is 1, but alpha 1 value 0 or 1. 0 or 1. Alpha 2 value either 0 or 1. That means alpha 1 ranges from 0 to alpha 1. Alpha 2 ranges from 0 to alpha 2. Therefore, it includes 1 plus alpha 1 values. It takes 1 plus alpha 2, 1 plus alpha 3 like this. Therefore, the total number of factors of this n is 1 plus alpha 1 into 1 plus alpha 2 into and so on 1 plus alpha k. Did you understand this? Alpha 1 ranges from, alpha 1 varies from 0 to alpha 1. Just like this. Here alpha 1 is 0. So here I wrote 0, 1, 0, 1. Alpha 2 is 1. So it can be written, you can write 0 or 1. That means alpha 1 changes from 0 to alpha 1. 0 to alpha 1, how many values are there? 1 plus alpha 1 values. Similarly, alpha 2 ranges from 0 to alpha 2. How many values are there from 0 to alpha 2? 1 plus alpha 2. So if you extend for alpha k, it ranges from 0 to alpha k. So the total number of values from 0 to alpha k is 1 plus alpha k. So like this, when n has a prime factorization like this, the total number of factors of n is 1 plus alpha 1 into 1 plus alpha 2 into and so on 1 plus alpha k. Provided that m has a prime factorization like this. Very, very important. Note this. Heading is Fundamental Theorem of Arithmetic. Fundamental Theorem of Arithmetic. Every natural number n greater than or equal to 2, every natural number n greater than or equal to 2 can be expressed as, every natural number n greater than or equal to 2 can be expressed as product of powers of prime numbers. Every natural number small n can be expressed as product of powers of prime numbers. That is n equal to this, where these are prime numbers and these are numbers. So write these points, this and this, followed by examples. Write this prime factorization followed by description and then examples 1, 2, 3, and then I will come back to the total number of factors of n. Now continue the point. Here the number of factors of n is, here the number of factors of small n, the number of factors of small n is 1 plus alpha 1 into 1 plus alpha 2 and so on into 1 plus alpha k. The number of factors of n is 1 plus alpha 1 into 1 plus alpha 2 into and so on into 1 plus alpha k. Highlight this. Because alpha 1 changes from 0 to alpha 1, alpha 1 ranges from 0 to alpha 1, comma alpha 2 ranges from 0 to alpha 2, alpha 1 ranges from 0 to alpha 1, alpha 2 ranges from 0 to alpha 2 and so on, alpha k ranges from 0 to alpha k. Now let us go through classroom workbook. So let us start from question number 41. The probability of getting 2 heads and 2 tails from 4 tosses of same coin. Coin is fixed, same one coin, but we were tossing a coin 4 times, 4 tosses. What is the probability to get 2 heads and 2 tails? Sequence is not an important. First and last outputs can be heads, middle tosses can be tails. So order is not an important, but the total number of heads is 2, the total number of tails is 2. So here that means we are tossing a coin 4 times. I am going to apply binomial distribution. Binomial distribution. So what n represents the number of times a trial is conducted. So coin is tossed 4 times. So assume that getting head is success, or getting head is tail is failure, whatever it is. So failure is, for example, tail. So you can feel getting tail is success or getting head failure, no issues. Now probability to get 2 heads. 2 heads. So the formula is actually 4C2 into P square into Q square. So this is 4C2 into the probability of getting single head is 1 by 2. So how many times head has to appear? 2, and tails has to appear 2 times. So therefore 2 heads and 2 tails. So 4C2 is 6 by 16. So this is 3 by 8. You can see, I will tell you, when a coin is tossed 4 times, you will get 2 power 4 sample points, 16. Out of 16, I will get 2 heads and 2 tails in 6 different occasions. Let me write these 6. So like this, HHTT, HT, TH, like this. Or you can go for permutations. This is very simple. Permutations. How many symbols are there? 4 symbols. So 4 factorial divided by H is repeated twice, tail is repeated 2 times. So this is 24 by 4, this is 6. That 6 is nothing but this 6. So sequence is not an important. So you need to get 2 heads and 2 tails in any sequence. So first and last can be heads, middle 2 tosses can be tails. First 2 tosses can be tails, last 2 tosses can be heads. Sequence is not an important, only count is important. You must have 2 heads and 2 tails. So probability of getting 2 heads. 2 heads means remaining 2 tails. So 4C2 into P square, 2 times heads and remaining 2 times tails. Probability of getting head is 1 by 2, single head. Probability of getting single tail is 1 by 2. So 6 by 16. I wrote you 16. So the required probability is 3 by 8. Read out question number 42. Assume that the probability of SA, South Africa, winning the game against IND, India, is 1 by 3. The probability of South Africa winning the game against India is 1 by 3. So that is probability of winning the game is 1 by 3. Not winning the game is 2 by 3. So because Q is 1 minus P. So if South Africa plays a 3-match cricket series against India, the probability that South Africa wins only 1 match is, so there is a 3-match series between India and South Africa, but out of 3-match series, South Africa has to win only 1 game. Instructions are given. Assume that no matches are tied and abandoned. So no match is tied, no match is cancelled out. So all 3 matches have been scheduled very properly, right? So therefore, out of 3, so South Africa has to win only 1 game. So therefore, probability that South Africa wins only 1 game against India. So only 1 out of 3 matches. 3C1 into P power 1 into Q square. So South Africa has to win only 1 game and India has to win remaining 2 matches. So 3C1 into P is 1 by 3 and Q is 2 by 3. So 2 by 3 whole square. But here 3C1 is 3 into 1 by 3 into 4 by 9. 3 will be cancelled. So it is 4 by 9. So they asked us answer up to 3 decimal place.